So this is day 2 of optimization, and if you're interested in the optimization problems, I would advance the video on. If you're in my class, I want to review the warm-up that you were asked to do. Hopefully you worked with some of your classmates to work on that. So let's just jump in, and in this problem you can see that you are given an x value of pi in a function named f and a y value output of 1. You are also given that the first derivative of this function f at pi over 8 is equal to 0, and you are given the equation of the first derivative. So job number 1 is, oh, by the way, that also tells us that pi over 8 is a critical number since the first derivative is equal to 0, and we'll see how all this plays out. So find the linearization of f at x, or find the linearization of f at pi. So linearization tells us to write the equation of a tangent line. So I'm going to substitute the x value of pi, the given value of pi, in place of x. We're given the y value of 1, which is substituted here. And we're going to substitute pi into the first derivative, which is given to be here. And when you find f prime of pi, you get a slope of 2. So this is right here, the slope of my tangent line, slowly and carefully going through the trig. And so I substitute 2 in place of m, and I need an m right there. Let's throw that in there. And so that is the linearization, writing the equation of the tangent line. For letter B, we're looking for whether or not the approximation of a number really close to pi, we're adding 0.001, using the equation of the tangent line would be too small or too large. Notice it does not say find the approximation, it says would the approximation be too large or too small. So to determine that, we're going to need the concavity of the original function. To determine that, we're going to need the second derivative of the original function. I have the first derivative here. So we're going to need to produce the second derivative. Please pay close attention to the fact that right here we're going to need a chain rule, and right here we're going to need a chain rule. So when we substitute that into, well, first we're going to find the second derivative. I think I do that right here. Let me slide this over and then slide this down. So using the chain rule, the second derivative is -4 cosine 2x minus 4 sine 2x. Substituting in pi, we get an outcome of -4. And since the second derivative is negative, that tells us that f is going to be concave down, which means the tangent lines would be above and the approximations would be too large. So hopefully that's what I said. An approximation of f of pi plus 0.001 using the equation of the tangent line would be too large because the second derivative at pi is less than 0. So f of x is concave down at x equal to pi, and the tangent line is above the original function. And then lastly, letter C, determine whether or not there is a local max or a local min at x equal to pi over 8. So you will recall back in the very beginning that you were given that pi over 8 is a critical number of the original function. We cannot make a number line. I guess we could, but we don't know if pi over 8 is the only critical number. So I would not recommend doing all of that crazy trig work to see if there are other critical numbers. What I really would recommend is going to the second derivative test, because in the last problem we just figured out the second derivative. So the smart thing to do in this case would be to substitute the critical number of pi over 8 into the second derivative. So when I do that, there's my second derivative. When I substitute pi over 8, notice that when I reduce, that becomes pi over 4. So it becomes one of our special angles. And, whoops, my radicals moved. So we'll fix that in a second. So so that's my simplification. Let me slide this down. My radicals slipped or moved, or I'd moved something. The cosine of pi over 4 is root 2 over 2. The sine of pi over 4 is root 2 over 2. So when we have a negative and a negative, we get a negative, which is less than 0. I don't really care what the actual number is. I mean, it's negative 8 root 2 over 2, which is less than 0. So since the first derivative at pi over 8 equals 0, making pi over 8 a critical number, and the second derivative at pi over 8 is negative, that tells me by the second derivative test that I have a local maximum on f at x equal to pi over 8. So hopefully you were working, if you're in my class, with your classmates looking at the previous night's homework. The answers were posted. In this video, I'm not going to walk through each of those problems, but what I am going to do is to go ahead and jump in and do I think it's 3 more problems. Yes, 3 more problems of a different nature that hopefully will help you to be able to work on some optimization. So remember, in optimization, your goal, our goal, everyone's goal is to find either the maximum or the minimum. Optimization is an application of the extreme value theorem. Okay, so let's jump into this problem. A rectangle is to be inscribed into a semicircle, meaning a rectangle is going to be put inside of a semicircle, and the semicircle has a radius of 2. What is the largest or maximum area the rectangle can have, and what are its dimensions? So hopefully you can see right away our job is to maximize the area of the rectangle. Now before I write I know that the area of a rectangle is base times height, but I'm going to draw up this situation. So notice I'm going to, it's going to be convenient to actually create the semicircle on an XY axis. Remember, the semicircle had a radius of 2. So I'm actually creating a semicircle. There's radius of 2, radius of 2, radius of 2. And then I'm going to inscribe or put a rectangle inside of the circle. Now the convenience of doing that is this. So take a look right here. Since we're starting at the origin, the distance from here to here, and remember we don't know how long that rectangle is, that distance from 0 to here is x. So if the distance from 0 to this point right here is x, then all the way across the rectangle, the length is 2x. The height of the rectangle is this distance right here, and I'll notice that the height of the rectangle is touching the semicircle. So the equation of the semicircle is the y value. So the area of the rectangle, if x is the distance from the origin to one end of the rectangle, then the length of the base, as I set up here, because from the origin to the right side is x, then from the origin to the left side also has to be x. Therefore, the entire length of the rectangle is 2x. The height of the rectangle is the equation of the semicircle. So watch what I do here. Since the radius of the semicircle is 2, the equation of the entire circle, a whole circle, would be x squared plus y squared equal to 2. Now, I'm going to get y by itself so I can figure out the height of the rectangle. So I subtract x squared from both sides and take the square root. So right here, x squared plus y squared is equal to 2 squared. 4 minus x squared, and I take the square root. And since I didn't do a plus or minus, some of you may be going, oh, you forgot your plus or minus. You've been taking points off my paper. Well, I don't want a plus or minus because I only want the top half of the circle. So I intentionally did not do plus or minus because this is the top half of the circle, which gives me a semicircle. So the height of the rectangle is the y. This expression right here is the height of the rectangle. All right, that was a lot of work just to get to the area of the rectangle. Now the area of the rectangle is base times height. So we said that in our problem, the base is 2x. So I start with base times height. The base of our rectangle was 2x, and the height of our rectangle was 4 minus x squared to the 1/2 power. That's the equation that I want to maximize. It already has one variable. I've already taken care of that with my helper equation. Now I need to find the derivative. It is a product, so I'm going to use the product rule. Now I know a lot of you like crisscross applesauce, so over here to the side you could do 2x, and over here you could do 4 minus x squared to the 1/2 power. The derivative of 2x is 2. Using the chain rule, I get 1/2, leave the inside alone, to the negative 1/2 power times the derivative of the inside, which is negative 2x. The 2 can divide out with the 2. So then I can find my derivative by crisscrossing and adding. So the first derivative, there's my 2x times all of this over here, and I didn't simplify, plus 2 times 4 minus x squared to the 1/2 power. That's my crisscross applesauce. Let's do some cleaning because we have to set this equal to 0. So what did I do? I have a negative 1/2 power here. So I'm taking that to the denominator. This 1/2 divides out with the 2. That leaves me with this 2 right here. I have x right here times negative x right here, which gives me the negative x squared. That's the cleanup for term number 1. In term number 2, as I already showed you before, 1/2, the 2 divides out with the 2, and that leaves me with oh wait, sorry, that was from right here, so my bad. So that one, nothing moves, everything is fine from there. Okay, to solve this equation, I'm going to take the negative 2x squared over square root of 4 minus x squared, add it to the left-hand side so that I can do cross multiplication. In other words, that's over 1, and I can cross multiply. And of course you can stop this video and do a little bit and then check a little bit, see how you're doing. By the way, right here, if you're wondering, the 2's divide each other out, so that makes life easy, and that's where the x squared over here came from. And then when I multiply 4 minus x squared to the 1/2 times 4 minus x squared to the 1/2, the 1/2's undo each other and take the radical off, and I get 4 minus x squared. So what looked like it was going to be kind of ugly and difficult to manage is really not that bad. I'm going to add x squared to both sides and divide by 2, and then take the square root of both sides, and I get plus or minus square root of 2, or 2 to the 1/2 power. I need help. Getting a negative value does not make sense. Remember, that was part of the reasonability. So even though I got plus or minus, this doesn't make sense because x is the distance from the origin to one end of the rectangle. So really x is equal to the square root of 2, but that means that the length of the rectangle would be 2 square root of 2. To get the y value, I'm going to substitute the square root of 2 in here. So the square root of 2 squared is just 2. 4 minus 2 is 2. So in other words, rectangles, as you see, maximizing areas of rectangles every time gives us squares. So the dimensions that maximize the, what am I trying to say? Trash can. The dimensions, I think that's 2 to the 1/2, not 2 to the 3/2. Oh yeah. So it's really 2 to the 3/2. That's the x coordinate, so that's the same thing as 2 root 2 to maximize the area to be 4. Next problem excuse me, problem number 8. An open box is to be made from a 16 by 38 inch piece of cardboard by cutting out squares of equal size from the 4 corners and bending up the sides. So we're starting with a 16 by 38 piece of paper. If you think of it like that. So if you take a look, there's my 16 by 38 inch piece of paper. And I'm going to cut squares, cut a square out of this corner, a square out of this corner, a square out of this corner, and a square out of this corner. So what you would have is something, let's see if I can sort of draw it. You would end up with something that looks sort of like this. So that square is gone, and that square is gone, and this square is gone. Oops. And the square is gone, like that. So now you could fold, you have 4 flaps. This will be flap 1, a flap, a flap, a flap, and you could fold up the flaps and actually make a box. So that's what's going on. So the question is, what size cut should you make? How big should your squares be to maximize the volume of the box, okay? So now the size we're going to cut, I'm letting be x. I don't know what size square I want to cut. So this is x by x. And this is going to be x. And this is going to be x. And this is going to be x. And this is, you get the idea. So the length of the box, think about this. We know that volume is length times width times height. The length of the box, it used to be 16. We had a 16-inch piece of paper, but we're cutting this part out, so that's 1x that's gone. We're cutting this part out, that's 1x that's gone. So the length of the box actually is 16 minus 2x. We cut out 2 x's, 1 from each corner. All right, I already said all of that. And that doesn't matter whether you call it the length or the width. Now the height of the rectangle or the length, whatever you want to call it, is the 38. So the piece of paper was 38 inches all the way across, but we're cutting out an X on this side, and we're cutting out an X on this side. So that's 38 inches originally. Cut out an X is 38 minus 2x. And the height of the box is what you get when you fold up the flaps. That would be the size of the cut that you make. So that's x. So there's the length, the width, and the height. Now we're trying to maximize the volume of the box, and so we said the volume of a box is length times width times height. Our length is 38, take out 2x. Our width is 16, take out 2x, and our height is x. That's our primary equation. Now, good news, bad news, a lot of algebra time. So what I'm going to do is I'm going to have to, and I'll use a calculator to support me, I'm going to have to FOIL these 2 binomials and then distribute the x. So you can stop, take the time to do that. When I do, when I FOIL the 2 binomials together, which is really multiplied by distributing, I get 608 minus 108x plus 4x squared. Now I'm going to distribute the x, and I get 4x cubed minus 108x squared plus 608x. Primary equation. Lots of algebra. Now the calculus. First derivative, because we're doing EVT, set equal to 0. So the first derivative is 12x squared minus 216 plus 608. And this is definitely going to need some calculator work. That does not simplify. I can't divide anything. I mean, I guess I could divide everything by 2, but I'm giving you permission to use your calculator to graph this and figure out where the parabola crosses, because I think this is going to be decimals. I don't think it's going to factor. So the way that you're going to do that on your calculator, smart people, is you're going to substitute or type in y1 is quadratic, y2 is 0, and you're going to do an intersection to see where the parabola intersects the x-axis. I think you're going to get a positive and a negative, and of course the negative doesn't make any sense to this situation. So there's me repeating how you do this on the calculator. Then you're going to do a second calc number 5, and I correct. One of the numbers is negative, doesn't make any sense. So x is equal to 3.492. Make sure you're stopping the video, checking that. And then I'm going to find there's just a graph to show you what it looks like on your calculator when you graph it. Oh no, actually the other number is not negative. We get 3.492. The other number is over here between 14 and 15. But think about it, you can't cut a square 14, you've only got 16 inches on this side to work with. So you could not cut a 14 by 14 square. You couldn't cut a 14 inch on this side and 14 inches on this side. You don't have enough paper to do that. So it's an unreasonable value in the domain. And what's under here? Nothing else. And then my sentence, the dimensions of the square are 3.492 by 3.492. And lastly, on page number 8, problem number 5, this one's going to need a lot of slow reading, a lot of sketching, a lot of drawing to figure out what's going on here. So hang tight, hang with me. An offshore oil well is located in the ocean at point W, 5 miles from the closest shore point on a straight line shore. The oil is to be piped to a shore point, B, that is 8 miles from A, by piping it on a straight line underwater from W to some shore point P between A and B. That's a lot of words. So first of all, I'm going to create my shoreline, and then I'm going to put my oil well in the ocean at point W. So I have a point A, I have a point B, where the goal is that's where the oil is going to get pumped, and then we're going to have a point somewhere between A and B where we're going to pump the oil. So my diagram looks something like this. So this is the shoreline. Point A is where we're going to pump the oil directly to. Point B, I'm sorry, that's not where we're pumping directly to. Point A is the distance from that the oil well is from the shore, which is 5 miles. Where we want to get the oil to is point B, which is 8 miles away from point A. And there is a sweet spot, point P, where it's most economical to pump the oil underwater to point P and then pump the oil directly from point P on the shore to point B. So that's our situation. A and B are 8 miles apart. A and W are 5 miles apart. I do not know how far P is away from A, nor do I know how far P is away from B. So I'm going to let the distance from A to P be X, which means that the distance from P to B is 8 miles minus X. Now I could have reversed those two values. I could have made this distance X and this distance 8 minus X. But when I do my Pythagorean theorem work to figure out the distance that I'm going to pump the oil underground, then this relationship would be much messier if I had this as 8 minus X. Because this distance of this hypotenuse of this right triangle is the square root of x squared plus 5 squared, and that's where the 25 is coming from. So by the Pythagorean theorem, I know that x squared plus 5 squared is equal to, I'll put a question mark, that squared. So the distance from W to P is represented by the square root of x squared plus 25. So these are the distances that I'm dealing with. Now that was just to get the problem set up. Now I'm going to bring some money into the problem. If the cost of laying pipe is $100,000 per mile underwater, so when I pump oil through the pipe, right here, it's $100,000 per mile. When I pump oil on the shore from here to here, it is $75,000 per mile. The question is, where should I place point P? Where between A and B should point P be located to minimize the cost? So our goal is to create a cost equation. So it's going to be 100,000 multiplied by this distance plus 75,000 multiplied by this distance will give me the total cost. So let me do some cleaning up by getting rid of a few of these boxes. No, wrong one. Get rid of that box right there. Goodbye. And now let's start uncovering my primary equation. Notice that I'm using 175. Since it's 1,000, I can drop those zeros and bring them back in at the end, and it makes my arithmetic much easier. So 100 times underwater distance plus 75 times the land distance gives me 100 times the underwater distance from my Pythagorean theorem, 75 multiplied by the land distance from P to B. There's my equation. Now it's calculus time. I'm going to take the first derivative using the chain rule. So half of 100 is 50 to the negative 1/2 power times the derivative of the inside minus wait, is that right? 75. Oh, yeah, because 75 times 8, the derivative of constant 0, minus 75, yeah. Brain freeze there. We're going to set that equal to 0 and move some things to the denominator because we have negative powers. Add 75 to both sides, and you can put a 1 under that for cross multiplying. Okay. Divide both sides. Let's see what I want to do here. Yeah, divide both sides by 75. And I reduced, when I divided both sides by 75, I reduced that by 25 to make it 4x over 3. Square both sides. Probably, I'm guessing my next move would be to multiply both sides by, no, I didn't. Subtract x squared from both sides. So since this is 16x squared over 9, that would be 16x squared. The subtraction would be 16x squared over 9 minus 9x squared over 9 to make a 1. And that's where the 7 over x squared comes from. Multiply both sides by 9. 9 times 25, that's 9 quarters. So 225. Divide by 7. Square root both sides with the calculator. A negative distance would not make sense. So in order to minimize my cost, I should put point P, 5.669 miles, away from point A, and that would minimize my cost. Point P should be located 5.669 miles from point A in order to minimize the cost. Okay, so again, you just got to dig in. You just got to do the problems. You got to go through the algebra and take your time. So your work now and tonight is 5 more of these. So 20, 22, 23, 24, and number 27. Solutions are posted, and if you look on the YouTube page, not only do I have my video of 2 videos of optimization, I have additional Patrick JMT videos where he works out specific types of problems like a rectangle inscribed, maximizing the area of a fence, a box with cutout corners, maximizing a can, surface area of a can. So take a look at those. They might be beneficial for you.